Hey everyone, and welcome back to Conquering Chem. My name is Nathaniel McLean, and today we'll be on part 4 of this chapter 1 series, part 4 being about uncertainty in scientific measurement. Just in case you missed it, part 1 was on the classifications of matter, part 2 we spoke about SI units and dimensional analysis, and part 3 we spoke about density and percent composition. So if you need help on any of those, I welcome you to check out my videos, and I will leave the playlist for those videos somewhere in the corner of this screen, so check those out if you need them. Jumping right into it, when we look at uncertainty in measurements, we first have to look at a few definitions. So we're going to look at error, and we're also going to look at accuracy and precision. So when we look at error, there are usually two types of errors that we will face in general chemistry. We have systematic error and random error. So systematic error, before we go deep into the definition, we usually relate that to errors that occur because of the instrument itself, while random errors tend to be human errors because it has something to do with our own experimental skill. So looking at the definitions now, we see that systematic errors are those that have inaccuracies that occur in a consistent range and direction. For example, if we have a scale that always reads 1 to 2 pounds heavy, that would be called a systematic error, mainly because it is reproducible. Because if you know that it's always 1 to 2 pounds heavy, you can always adjust for that in your calculations. On the other hand, random errors tend to be inaccuracies that are due to the limitations in experimenter's skill. For example, not being able to read the meniscus in the same way. So let's say you're measuring a volume of something, and one time you have 10.10, the other time you think it's 10.12 milliliters, and the other time you might think it's 10.09. That has to do with you not being able to read that little line at the bottom properly. So that has nothing to do with the instrument, but it has something to do with you. And you can't really adjust for that in your calculations because it's random every time. So remember that systematic errors tend to deal with the instrument, while random errors are human errors. When we look at accuracy and precision, we know in the English language we tend to use them interchangeably, but in science they're a little bit more specific. So accuracy, the definition for that is the closeness of a result or reading to the true value or accepted real value, while precision is the closeness of measurement to each other and the degree of reproducibility of a measured quantity. And we'll look at those in a little bit more detail in a diagram that I have on the next page so that you can put the definition with the diagram. But just remember that in an ideal situation, we want our measurements to always be accurate and precise, but a combination of them can exist at any time. So looking at this diagram, we can see how a measurement can be precise but not accurate. Over here, we have a bunch of shots here on this bullseye. All of them are close together, so that represents high precision, but since they are far from this bullseye, they're not accurate. On the other hand, we have these shots which are all close to the bullseye, meaning they're accurate, but they're not that close together, meaning that they're not precise. In the worst case, we can have measurements that are scattered all over the place and away from the bullseye, meaning they're not accurate and not precise. Or we can be a top shotter like me and have all of the measurements in one position, in the middle and close together, making them both precise and accurate. Now, as we jump into significant figures and exponential notation, I want to start with significant figures. Now, significant figures, they determine the degree of certainty of a measurement or measuring device. It also determines how many figures should be expressed for a calculation. The definitions aren't really that important for significant figures. What is important is making sure that you know how to represent the correct number of significant figures or identify how many significant figures are given in a given value. So let's look at this example. It reads, after measuring a length of string with a ruler 3 times, you get 3 different measurements, 25.56, 25.57, and 25.54. Now, the significance here is that yes, we have 4 significant figures, but that last digit, the 4th digit, tells us that at some point there is some error, some inconsistency that's going on, because of course, we're not measuring the string in the exact same way every time because we're only human and we can't reproduce that. You might be wondering how you can measure a string round. You might be stretching it differently each time. You might put the ruler down differently each time. Who knows? Point is that 4th digit in each case, in this case the 6, in this case the 7, and in this case the 4, that shows us where the uncertainty occurs. That is the significance of significant figures. It really tells us the uncertainty. But what's more important, as I said before, is being able to see how many significant figures are in a given value and work it out for ourselves. And there are a number of rules for that. So the first rule is that the zeros at the beginning or to the left of a given number are not significant. The second is that all non-zero integers are significant, non-zero integers being numbers 1 to 9. Number 3, all zeros between non-zero integers are significant. And number 4, all zeros placed at the end or to the right of a given number are also significant. And we can see how this plays out in the examples following. So the first example has the number 10,000. We know that 10,000 has 5 digits, 1 and then 4 zeros, but how many significant figures are there? Now there are 5 significant figures because the first number all the way to the left is an integer, so that starts our count. And all the zeros after that are following the integer, meaning that those are also significant. So we have 1, 2, 3, 4, 5 significant figures. In the next example, we have something very similar. We have 5 digits, 5 significant figures. Easy peasy. The next one might be a little bit confusing if you're first being introduced to significant figures. We have the number 0.002100. Now we're told here that it has 4 significant figures, and this is why. The first rule says that all zeros to the left of the value given are not significant. So all of these don't count towards how many significant figures you have. However, you get to your first integer, in this case it is 2. Everything after that is significant, even the zeros. So we have the 2, which is 1, next figure 2, then 3, 4 significant figures. The next example shows you what happens if the zeros are between integers. Of course, there are 5 digits. The zeros are in between, meaning that we have 5 significant figures because all zeros between integers are significant. The next one, we have zeros at the beginning or to the far left and zeros in the middle. Remember that the ones to the left are not significant, while the ones in the middle are significant, giving us 4 significant figures. And in this final example, we have everything being thrown in there, the most difficult example you could possibly see. We have zeros to the left, zeros in the middle, 0 at the end. The zeros to the left, again, they don't count. Those are not significant. We start at the first integer. In this case, we have a 1, and we count 1, 2, 3, 4, 5. So we have 5 significant figures. Again, because the zeros in the middle are significant, and all zeros to the right of the value are also significant. Now jumping into exponential notation, also known as scientific notation, is usually just a way to express large values by only taking up a little bit of space. And we can jump straight to this example here. Instead of writing the number 1 million, which has 7 digits, we can simply express that as 1 times 10 to the power 6, and I'll show you how in a second. The next example, we have 0.00146000, and we can easily express that in a shortened term as 1.46 times 10 to the minus 3. Let's consider this larger example at the bottom. We have 0.00146000. You would always start at the decimal place. And once you're there, you want to jump in the direction that would take you to the right side of the leftmost integer. In this case, the leftmost integer in this value is going to be our 1. So the exponent that's attached to 10 has something to do with how many times you jump from the decimal place. So in this case, we start at this decimal place and we jump 1, 2, 3 times before we are to the right of the leftmost non-zero integer. So basically you jump with your decimal until you have only one single integer to the left of that decimal place. So looking here again, we jump 3 times, 1, 2, 3. Since we jump to the right, we have to make it a negative number. So we express this as 10 to the minus 3. If we had went to the left, it would be a positive number. In the case here with the 1 million, we could imagine that a decimal place was placed right here. And we jump backwards 1, 2, 3, 4, 5, 6. And we stop here because we now have a single non-zero integer to the left of our decimal place. Since we jump backwards 6 times, or we jump to the left 6 times, our exponent is going to be positive, and it's going to be 6. And finally, the rules for determining the number of significant figures or decimal places when doing arithmetic. The first rule applies to whenever you multiply or divide values. And it reads, when multiplying or dividing, the result must have as many significant figures as the least precisely known quantity in the calculation. And we can see that in the example below. We have 15.025, which has 5 significant figures, being multiplied by 4.5, which has 2 significant figures, giving us an answer of 68 meters squared. 68 has 2 significant figures, and that makes sense because the least precisely known quantity had 2 significant figures. The next rule applies to when adding or subtracting, and it reads that when adding or subtracting, the result must have the same number of decimal places as the quantity with the least known decimal places. So looking at this example, we have 5.4337, which has 4 decimal places. We add that to 3.42, which has only 2 decimal places, giving us an answer with only 2 decimal places because the quantity with the least known decimal places had only 2 decimal places. This finally brings us to the end of chapter 1. I would like to take the time now to thank 3 of my friends in particular who helped me with this project that I've started, tutoring chemistry online. I would like to thank Terrace Black, Taishik Battle, and Montaze Cooper. They were all great encouragements to me in starting this, and beyond encouraging me to start this, they also help provide the equipment. So the tripod, I got it from Terrace. I got a whiteboard, which you can't see yet because we're not using it. And I have this 2D thing covering the screen over it. But he got a whiteboard for me, which you'll see in the tutorials. And I'd like to thank Montaze for getting me a ring light so that I won't be in the dark while making these videos. So I would like to thank them, 2 of them in particular, Terrace and Montaze. Both have their own talents as well. Montaze Cooper this year became an author as he published his first book. I'll leave the description down below so you can get in contact with him and visit his website to purchase one of those books. And Terrace, he's a great visual and performing arts person. He's great at dancing, great at singing, great at songwriting. He's just got all the things that I can't do. So I'll leave his description below, his Instagram, and also the link to his SoundCloud so you can listen to his music. I'd like to thank them a lot. If you're watching, thank you. And thank you to everyone who is here to support, as well as those who are being supported by this. I hope that it helps you with your general chemistry. Again, feel free to follow me on my Patreon, where you can have early access to my chapter materials, as well as be able to download my PowerPoints and tutorials. Without further ado, I've kept you here long enough. Thank you again. My name is Nathaniel McLean, and this is Conquering Chem, your #1 stop for general chemistry tutoring. Thank you.